Welcome back! In this video we dive deeper into the sources that create thermal loads inside buildings. From people to sunlight, from infiltration to lightning, each factor affects how much heating or cooling space we'll need. You'll learn how to recognize these contributors and conceptually estimate their impact using standard values and simple methods. Here's what we'll cover in this video. We'll start by distinguishing between sensible and latent loads, a critical concept in HVAC. Then we'll look at internal gains like people and equipment, before exploring how air movement and envelope design also affect thermal loads. Let's get started. In this video, you're going to level up your understanding of thermal loads. You'll learn how to identify and estimate internal and external heat gains from people, lights, and equipment to solar radiation and infiltration. We'll also show you how to use simple formulas and standard reference values to make solid early-stage HVAC design decisions. Let's dive in. Imagine walking into a classroom full of students in the afternoon sun. It feels hot and stuffy. But why? What's adding heat to the room? These questions get at the heart of today's topic: internal and external sources of thermal loads. Thermal loads can be divided in two main types: sensible and latent. Sensible loads involve changes in air temperature and are the most common type in HVAC calculations. Examples include sunlight heating a room or heat from computers and lights. Latent loads, on the other hand, involve moisture. When people exhale or sweat, or when outside humid air enters a cooler space, moisture must be removed by the HVAC system to maintain comfort. It is important to distinguish between these two types of loads because they affect HVAC systems designed differently. Let's look at internal gains, starting with people. Occupants contribute both with sensible and latent heat to the space. The amount depends on the activity level, and values are well documented in standard reference like ASHRAE Handbook Fundamentals. For example, a seated adult typically emits 75 watts of sensible and 55 watts of latent heat, according to Table 1 in Chapter 18 of the 2021 edition. For equipment like computers, printers, and appliances, the heat is mostly sensible. The SRI Handbook Fundamentals Chapter 8 provides heat gain estimates for a wide range of equipment. A simple method is to multiply the equipment's rated power by the use factor, usually between 0.5 and 1, depending on how often and how intensively it's used. This gives a quick estimate to estimate internal heat gains for design purposes. The primary source of heat for lighting comes from the light-emitting lamps, but additional heat is generated from ballast and other components of the luminaries. The sensible heat gain from lighting can be estimated with this formula, where W is the total light wattage, and one factor is the lighting use factor, ratio of wattage in use to total installed, and the other one is lighting special allowance factor, with the occupants for power consumed by ballast and any other effects. For example, for incandescent lighting, the special allowance factor is 1. For fluorescent systems, this factor adjusts for ballast power. For high-efficiency electronic ballasts, this value might be slightly less than 1. These adjustments ensure that the actual power converted to heat is properly estimated. Ventilation and infiltration bring outdoor air into the building. This air often needs to be heated or cooled, depending on its temperature and humidity. This introduces both sensible and latent loads. Ventilation refers to the intentional introduction of outdoor air, typically controlled through ducts and mechanical systems. Infiltration, on the other hand, is unintentional and occurs through leaks in windows, doors, and openings. While ventilation is easier to quantify and manage, infiltration varies with wind speed, building thickness, and pressure reference. A simplified formula for estimating the sensible heat due to infiltration is this one, where Q is the heat gain, ACH is the air changes per hour, and V is the volume. The factor 1.2 approximates the air densities and specific heat. For latent heat gain due to infiltration or ventilation, a separate formula based on moisture content will be used. SRI-Hamburg Fundamentals, Chapter 16, provides typical ACH values by space type. For example, residence can be between 0.35 to 0.5 ACH, offices between 0.5 and 1.0 ACH, and restaurants between 1.5 and 2.0 ACH. Also, SRI Standard 62.1 establishes minimum ventilation rates for indoor quality and occupant health. These rates are based on space type, occupancy, and activity level, and are crucial in HVAC design to ensure health as well as comfort. Solar and envelope gains are driven by building's design. Solar heat enters through windows and depends on area, orientation, shading, and glazing type. A simple formula is this one, where HHGC is the solar heat gain coefficient, which depends on the type of glazing, frame design, and shading devices used. Heat also transfers through walls, roof, and glass by conduction. This is calculated with this formula, where U is the thermal transmittance of the wall, A is the surface area, and delta T is the temperature difference. These are foundational to understanding building load. Typically, SHGC can be found in SRI-Hamburg Fundamentals Chapter 15 for various windows and glazing type. For U values of walls, roofs, and opaque assemblies, refer to Chapter 26 of the same handbook, which provides detailed tables based on construction materials and insulation levels. To sum up, buildings get heat from people, lights, machines, air, and the sun. Each source contributes in different ways, some through sensible heat, which affects temperature, and others through latent heat, which affects humidity. HVAC systems must be designed to handle both types. Conceptual estimates using simple equations and the standard values can go along toward better system planning. You've just explored the main contributors to thermal loads and how to begin estimating them using real-world references and simplified methods. In our next video, we'll connect those loads to design the decisions like window placement, orientation, and thermal mass. Later, we'll explore advanced techniques to estimate and control loads in real projects. Stick it with your building design intuition that will power your HVAC expertise.